Hello, everyone, and we are back after a little break. Had to lock in and focus on college essays for a little bit, but now that those are mostly done and almost all my applications are in, back to fun math. Yay, no more writing essays. I'm so happy. I'd much rather evaluate a summation. But anyway, um, what we have here today is a sum that I saw on my YouTube feed for specific value of a, but I thought it would be quite fun to evaluate it for just any integer a. So without any further ado, let's get to it. The first thing we're going to do actually is look at this j to the a. And one way we can write, j to the a is just, well, j to the a minus 1, but then just times, haha, not a, that's great, times j, right? Just by properties of exponents. And the interesting thing here actually is what happens to our sum. Our sum then becomes the sum from j equals 0 to infinity of j to the a minus 1. But note here that we have a j factorial in the bottom, which can be expanded, right? Which can be expanded as j times j minus 1 factorial. And as such, we see that we have a j in the numerator, j in the denominator, and those cancel. So what this leaves us with is a j minus 1 factorial. And sure, you might get upset a little bit here and say, oh, well, we have a negative 1 factorial in the denominator. But one way we can actually just define that is 0, because whenever we have 1 over, say, a negative integer factorial, that's effectively like a 1 over infinity almost. Same concept. It's 1 over an asymptote. So it is going to go to 0. What this means is that whenever we plug in j equals 0, that term is just 0. So the sum is the exact same thing if we just wrote a 1 there. And because of that, we can just re-index it, right? We can say that now this is the sum from j equals 0 to infinity of 1 plus j to the a minus 1, and then divided by j factorial. And you'll see here that we're in a very similar place where we started, only that we have a plus 1 with the j in the numerator, and our exponent has decreased by 1. And the idea here is that we're going to expand it next. So by the binomial theorem, we have the following. We have our sum from j equals 0 to infinity, and 1 over j factorial, which I'll write out front. But then this 1 plus j term is going to be the sum from, say, k equals 0 all the way up to a minus 1 of j to the k. I'm not kidding. But that right there is our sum now. And rearranging, let me scroll down. Rearranging, we find that this right here is sum from k equals 0 to infinity. Or sorry, not to infinity, pardon me. A minus 1. A minus 1. Oh, pardon me. I forgot the most important part here. There is an a minus 1. Choose k. That bit is slightly important here, actually. Yeah. Yes. Many apologies there. Okay. That is actually our sum, which whenever we switch the order of the sums around, because they don't really depend on each other, right? We end up getting this, and then times the sum from j equals 0 to infinity of j to the k, no joke, over j factorial. And you'll see here that we have something quite similar to what we started with. If I scroll up, we see here that it's effectively in the same form. But the interesting part here is that we've almost decreased the power, we've effectively decreased the power of j by 1. The reason for that is because k only ranges from 0 all the way up to a minus 1. So k having a max of a minus 1, we've decreased it because we started with a right there. So let's do something similar again and see where this pattern can lead us. We're going to say this is now, so just focusing on the sum right here, we can say that this is the same thing. This is just similar as before. From j equals 1 to infinity of j to the k minus 1 over j minus 1 factorial. And then re-indexing, I'm not going to rewrite out the whole thing because it really is just the same thing we did above. We have 1 plus j to the k minus 1 over j factorial, right, going from j equals 0 all the way up to infinity. And doing the same thing really as before, we can expand this using the binomial theorem. We can say then that this is equal to, we still have our sum over j equals 0 to infinity, of course, but then, you know, I'm actually going to remember my binomial coefficients. J, k, we're going to do L equals 0 to k minus 1 of k minus 1 to L, so k minus 1 choose L, and then times j to the L divided by j factorial. And rearranging our sum in its entirety, we find that we have our sum. So I'll write our sum for j out front. Our sum from j equals 0 to infinity. But then we have our sum over j and L. So I'm just going to write all of our sums up front and then all of our terms. So we have, let me zoom in a little bit more. We have our sum from k equals 0 and also L equals 0 to, so for the k, it's going to be a minus 1. But then for L, it's going to be k minus 1. So this order of these sums does actually matter. And then we're going to have, let's see, a minus 1 choose k. And then we're going to have k minus 1 choose L. And then we're going to have our j to the L over j factorial. And here's the really interesting part. The pattern is just going to repeat and repeat effectively indefinitely until the sum right here, or that index right there, can only be 0. So what is our sum? That really is the question being asked here. And what it's going to be effectively is we're going to have a bunch of these sums right here. So all of these sums involving k's and l's, and maybe m's and n's and o's and p's and so on, right? Depending on how big a is. We're going to have a bunch of those. And then at the end, we're going to be left with, well, this exponent forced to be, well, 0, because eventually this number right here is effectively limited by this number right here. So, for example, if a is, I don't know, 1, for example, you know, we have the first sum over k is going from k equals 0, or let a equal 2 actually. This first sum is going from k equals 0 to 1. Then the second sum is going from L equals 0 to really just 0 because, you know, we plug in 0, that doesn't make sense at all. The most k minus 1 can be is 0, so the exponent is forced to be 0. So what we end up with is a bunch of sums. So we're going to have our sums over, you know, sorry, everything but j really. K, and then our sum over L, and then our sum over, you know, M, and so on and so forth, right? And then we're also going to have, you know, our appropriate choose functions inside them. We're going to have a minus 1k, then, you know, k minus 1 L, and the pattern's just going to continue, so dot, 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 dot. But then we'll be able to separate it from it one more thing, and that right there is our sum over j. So our sum from j equals 0 to infinity of 1 over j factorial, because the exponent there is forced to be 0. Considering that we've managed to kind of factor that out, like, what is that sum? And we know that this is just the power series for e to the x, and that right there is literally just e to the 1. So this right here is just e. So what this whole sum is just some number, some kind of big integer, multiplied by e. And what these integers are actually defined as, these right here, are the Bell numbers. So this is represented by a b, in this case ba, because we have a, you know, we have an a right there. That's what it's represented by. And maybe instead of just taking my word for it, we can do a little bit of induction. So one of the things that the recursion relation of the Bell numbers is that bn plus 1 is equal to the sum from k equals 0 all the way up to n of n choose k and then bk. So let's actually start with the base case. That might be easiest. So well, we already kind of did the base case. This right here is literally just a equals 0, so we end up getting, well, e. But in this case, we end up getting our Bell number, sorry, is really just going to be 1 because there's an implied 1 right there. So our base case is literally it equals 1, right? So yay, we have our base case. And I should note that b of 0 is just 1. So yes, our base case does actually work. So let's go on to sort of the next case. So scrolling on over. Let us now consider a similar sum. The sum from j equals 0 to infinity, but this time j to the a plus 1 over j factorial. What does this give us? Well, we know that this is just going to be the sum from j equals 1 to infinity of j to the a over j minus 1 factorial. And that we can, again, reindex this. So this is, again, equal to the sum from j equals 0 to infinity. We've already done this like 3 times, so going a little bit faster. 1 plus j all to the a minus 1, or sorry, just a, pardon me. Then divided by j factorial. And using binomial expansion, we know that this right here is the sum from j equals 0 to infinity. The sum from, I don't know, say k, equals 0 all the way up to a of j to the k over j factorial, and then times our a choose k. This right here, you'll see something very similar because, well, just take a look at this, rearranging it. That'd actually be more helpful to see this better. So let's put the k sum out front at first. So this is k equals 0 all the way up to a, and now we have a choose k, and then we have our sum from j equals 0 to infinity of j to the k over j factorial. So here's the thing. What we're assuming by our inductive hypothesis, or by inductive, our inductive assumption is this right here, that our entire sum, I never actually wrote this out, our entire sum is b a times e. This is our inductive That's our inductive assumption, that our sum is just equal to that. And what we see here is that this right here, this sum right here, that is just our sum, which is, e times b a, or in this case, it'd be bk. So factoring out the e, we find that we have, well, e times the sum from k equals 0 to a of a choose k, bk. But you'll also see here that by our recursion relation for the Bell numbers, that this right here is really just bk plus, or ba plus 1. So what we found, and effectively proven, is that the next term in our series is going to be e, and then times the 8th Bell number plus 1, or a plus 1th Bell number, pardon me. So that right there, ladies and gentlemen, or actually going off statistics, it is mostly gentlemen. You get the point. At any rate, we've proven that the sum from j equals 0 to infinity of j to the a over j factorial is equal to the 8th Bell number times e. I hope you all enjoyed this video, and I will see you all in the next one. Thank you for watching.